I think one of the biggest challenges, I think coolest outcomes, would be finding a way to incorporate everything that humans know about the state of the world into general modeling, because there are a lot of existing data sets. So can we actually start from what we know instead of starting from scratch?
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring the many ways we can harness the power of artificial intelligence to learn more about our world. I'm also in a personal quest to discover if AI will be more of a help or more of a hindrance to our work as geoscientists. Similar to the opening question our guest asked today, all artificial intelligence, or AI, started with a question. And this question was posed in the 1930s by scientists like Alan Turing, who wanted to know if we could create computers that could learn from experience. The answer, as we now know, is yes. But it was a long, winding road of experimentation, discovery, and stagnation that led us to this certainty. The first successful AI program was written in 1951 by British scientist Christopher Strachey and was programmed to play checkers. Yes, you heard that right, checkers. The 1950s and 60s were a time of excitement, with machines learning to play games and perform mapping tasks. In the geosciences, they used methods such as k-means, Markov models, and decision trees to do things like describe sediment deposit cycles. After a brief slowdown in AI development in the 70s, we were off to the races again in the 1980s, which included more pronounced use of neural networks to complete tasks such as nuclear monitoring. In the 1990s, machine learning switched gears from a knowledge-driven approach to the data-driven approach we take today. And in the early 2000s, scientists began to shift the tooling of AI and machine learning models. These combined shifts allowed for an increase in access to and adoption of both shallow and deep machine learning research. And in 2001, Torch, one of the first machine learning libraries, was released as open source. Initially written in a programming language called Lua, the re-implementation of Torch using Python led to PyTorch, and this is now one of the leading deep learning frameworks used today. PyTorch is a really important tool when it comes to machine learning because it combines many different features. For example, dynamic computation graphs allow for flexible and rapid prototyping. The API is intuitive and easy to learn, even for those of us less familiar with machine learning. And PyTorch also works with many different popular libraries. In addition, PyTorch functions on GPU acceleration, and most importantly, there's a large active community that's always improving this machine learning framework. While PyTorch is a framework for supporting machine learning algorithms, using it for geospatial data, which varies widely in its data collection methods, formats, and metadata, is not as easy. This is where TorchGeo comes in. TorchGeo is a domain-specific library for integrating geospatial data into the PyTorch deep learning ecosystem. Released in 2020, this exciting new library offers tools like data loaders, datasets, and image transforms that allow scientists like you and I to work with geospatial data, including multispectral imagery. TorchGeo is also the first library to provide pre-trained models for satellite imagery, making it easier to apply transfer learning to remote sensing tasks with limited data. Now, I just covered a ton of information using a lot of jargon, which is usually not my MO. But I promise if you stay with me, by the end of this podcast, you'll have a much clearer sense of AI in the geosciences, because today, we're speaking with one of the co-creators of TorchGeo to get all these concepts straight. Let's get started. This episode of Down to Earth is brought to you by the Geoscience and Remote Sensing Society's technical committees. As part of the world's leading professional association for the advancement of technology, the GRSS technical committees are innovation hubs, bringing together experts from around the world to forward cutting-edge geoscience research, development, and applications. To learn more and be part of the premier community driving the future of geoscience and remote sensing, visit grss-ieee.org and join a technical committee today.
How do you find interesting things in satellite imagery? How do you pre-train models that are usable by others to solve specific questions? How do you get by with little labeled data in places that we aren't able to get ground truth or in situ observations? There's tons and tons of open questions.
This is Dr. Caleb Robinson. He works as a principal research science manager in the Microsoft AI for Good research lab, where he co-leads the geospatial ML research group and is the lead researcher on the Global Renewables Watch, Rapid Damage Assessment, and Global Building Density Estimation teams. What makes Caleb's work unique is his interest in using machine learning to find new insights in what already exists.
Some of the ones that I'm most interested in are how can we mine the interesting parts of these enormous catalogs of remotely sensed data that we have available to us. As an example, the Microsoft Planetary computer contains over 54 petabytes of information. There's going to be an enormous amount of knowledge about the state of our world, how it's changing over time, what the effects of climate change may be. The list goes on and on and on, but it's all locked away into pixels, and coming up with methods that are able to understand that data at scale, find the interesting themes in it, are definitely the most pressing questions of our time, in my opinion.
These are some of the questions that led this incredible scientist to co-create Torch Geo, leveraging and expanding on already existing infrastructures so remote sensing scientists can glean more information from the pixels of our satellite images. Let's learn more about how machine learning is applied in the geosciences and the different projects Caleb is working on. Before we dive into your work, let's cover some basic terminology and what we mean when we say AI in geoscience. First, how do you define AI in the context of geoscience?
Yeah, sure. So I think geosciences are kind of broadly the study of Earth. AI is a very broad term. I like to go a little bit more specific with machine learning, which I see as really a set of tools that you can use to analyze data at very large scales in most cases. And I think these two fields fit together nicely because geosciences have a lot of data, and a lot of the modern ML algorithms are very data hungry. They're powered by large amounts of both unlabeled and labeled data. So it's a very good fit for purpose use of ML tools.
Caleb has specifically defined AI in the geosciences as machine learning here. So I want to clarify for listeners the subtle difference between machine learning and artificial intelligence. Technically, machine learning is a subfield of artificial intelligence and is the application of AI that allows machines to extract knowledge from data and learn from it autonomously. Basically, machine learning teaches machines how to perform tasks and identify patterns so they provide accurate results. Artificial intelligence, or AI, on the other hand, is a broader umbrella concept that allows machines or systems to simulate human intelligence to solve problems. Because machine learning is one of the most important ways that AI systems run, especially in the geosciences, many people use the terms machine learning and artificial intelligence interchangeably. But since they are not exactly the same thing, this is why Caleb has specifically defined AI in the geosciences as machine learning. Throughout this season, we'll be using the terms interchangeably, so hopefully that won't get too confusing. Now, back to the interview. What are some applications or uses of AI or machine learning in geoscience today?
Oh, there's a ton. I mean, there are a lot of really cool global applications of AI to satellite imagery that I'm really excited about. Global Forest Watch is an awesome product. The Allen Institute runs models on kind of all of Sentinel-2 and all of Sentinel-1 on a regular basis, which is very exciting. Our group has a product that we're working on called Global Renewables Watch, where we're using ML algorithms on PlanetScope data to identify solar photovoltaic farms and windmills across the globe and through time. So these kind of large-scale applications are the things that most excite me. But then from the completely other side of the coin, there's very targeted uses of AI with very high resolution imagery to solve local problems and like disaster response that I think are very cool too.
Definitely. So there are amazing applications, but it's also changing how we work with geospatial data in exciting ways, right?
Yeah, definitely. So I think a method that's very exciting to me is bringing humans into the modeling loop. At the AI for Good Lab, we work on a project basis with other groups. So you can think of nonprofits, conservation agencies, academic labs. And the goal is to apply AI to a problem that they have that they're an expert in with an attempt to solve it in sort of a for good type way. And the way that I think is most promising for that is bringing those experts as far into the modeling loop as possible. And to give you an example of what that looks like, one of the projects that I've worked on in the past is with marine biologists from NOAA who are interested in identifying whales in very high resolution satellite imagery. And the traditional way to do this is exhaustively look through every pixel in 30 centimeter imagery and try to find whales that are on the surface of water. And an alternate way to do this is create this modeling loop where you first identify interesting or anomalous points in the water, show those patches of imagery to the domain experts. They can classify whether it's a whale, sometimes even identify what species of whale it is based on geographic context, temporal context. And that greatly reduces the amount of time they spend looking at imagery and allows them to focus on just the parts that matter. So you have AI algorithms doing the anomaly detection, you have the domain expertise from the marine biologists, and you put those together and you have a now more scalable way to find rare species that previously wouldn't have been able to been monitored.
I think there are a lot of misconceptions by the public in terms of AI, especially in geoscience, because I think a lot of people would think that AI will automate everything. And I like when you said about keeping humans in the loop. Why is this important? I mean, it seems like a given, but I think we need to be clear about why it's important, because I think the why helps address some of the challenges.
Yeah, I think it's one of the most important things as someone who's coming from the AI with like a computer vision background. I'm not a marine biologist. I'm not a geoscientist. So I don't have the context that's very often important to tackling those problems. It's a tool that can be used to improve kind of our understanding of the world, but you always need the domain experts in the loop. I don't think there's a way to get around that.
Makes sense. And you work with a lot of different domain experts in your role as the principal research science manager in the Microsoft AI for Good research lab. So, give us a basic overview of the lab and what you do as part of the geospatial machine learning research group.
Yeah, so the AI for Good Lab is a philanthropic part of Microsoft. We're a group of just over 30 people from research scientists, data scientists, visualization experts, program managers, engineers. And like I described earlier, we work on a project basis. So we partner with other organizations that have some sort of domain expertise and a problem that if we can solve it together would really unlock and do a lot of good, have impact in the world. So I work on projects like that. Specific to the geospatial ML space, I co-lead the geospatial ML group with my colleague Anthony Ortiz. And we're really looking at projects that have global scale that you need to tackle with large amounts of satellite imagery, models that are able to generalize, but then also at a very, very local scale, how to respond in disaster response applications and do building damage assessments from satellite imagery that was collected hours or days after a natural disaster.
And what has been your most exciting advancement or development so far?
That's a good question. The thing that I'm most excited right now isn't one kind of specific research advancement. It's really putting together a lot of smaller pieces together in a building damage assessment toolkit. So here the idea is you need to train models or have a model that's able to identify damaged buildings in post-disaster satellite imagery. And you can do this with off-the-shelf methods. People try to pre-train models that work in any sort of disaster scenario. And sometimes those models work, But the toolkit that we developed, and really the workflow that we have developed over the past couple of years, allows us to quickly fine-tune models specifically to disasters as they happen, which really eliminates a lot of the uncertainty into whether your model is going to produce useful results or not. So now we're able to consistently identify damaged buildings after natural disasters and get that information to first responders as quickly as possible.
That sounds like a really useful toolkit. Can you give me an example of how it's used?
Yes, let me like unpack this maybe. So Hurricane Beryl affected the Caribbean in early July. I think it formed as hurricane late June. It was one of the quickest hurricanes to intensify from a tropical storm to a Category 5 storm, and it was the earliest to do so by a couple of months. And it passed through the island of Carriacou on July 1st. And we got satellite imagery from the damage that it caused kind of mid-afternoon, July 2nd, that came from Planet through their SkySat satellites. And then in just a couple of hours, we were able to run this workflow that I was talking about on the imagery, classify each building on the island as damaged, not damaged. We also estimate the extent of damage, and then pass that information off to different organizations that were aiming to provide aid on the ground. So close to 24 hours after the event happened, we were able to get geopackage results of where we thought damaged buildings were to the organization. And the way that happens is we can label a couple of examples of what damaged buildings look like in the imagery that we receive, and then use that to fine-tune a disaster response model that we can then run on the entire image to get results for.
Wow, that's an incredible turnaround. How accurate were the results in this case?
Yeah, great question. So in this particular case, we labeled by hand from interpretation of the imagery 5% of the building footprints, classified them as damaged or not damaged, and found that the kind of initial model that we trained was 88% accurate. In other places like Lahaina in Maui, after the wildfires that happened there last August, we had over 94% accuracy. The signal of damage in the imagery was extremely clear. And the important thing is really that we're able to consistently hit that high 80s, low 90s accuracy, regardless of where the disaster is. The workflow and the fine-tuning with few-shot examples to a specific disaster eliminates the uncertainty of, hey, is this pre-trained model that we have going to generalize to this new event? We know it's going to produce useful results because we fine-tune it to that specific event. And being able to fine-tune quickly to the new disaster then allows that generalization performance.
Very cool. Thanks for sharing these different applications of machine learning in AI. Now, you co-authored a recent paper titled Mission Critical: Satellite Data is a Distinct Modality in Machine Learning. What are you arguing in this paper?
So in this paper, we're really arguing that satellite data should be treated differently than maybe a standard image modality when it comes to machine learning research.
What led you to the realization that satellite imagery is a distinct modality?
I don't think it was like one moment where I woke up and I was like, wow, satellite imagery is a different thing altogether. It's really kind of incremental learning since I started working with this type of data, having to deal with problems of coordinate reference systems and large rasters. And that led to me trying to write PyTorch code that better allowed researchers to incorporate geospatial data to computer vision pipelines.
This, my friends, was some of the humble beginnings of what has since become Torch Geo. After the break, we'll learn more about Caleb's involvement in this important project, and we'll also dig deeper on why Earth observation data needs to be handled differently when using it with machine learning. So stay tuned.
Want to be at the forefront of geoscience and remote sensing innovation? Then join one of the Geoscience and Remote Sensing Society's technical committees. With 8 committees to choose from, you'll find your niche. From earth science, informatics to data fusion and climate technologies, our committees are driving progress and advancing the state-of-the-art in geoscience remote sensing work. Through our networks, you'll collaborate with global professionals, participate in cutting-edge research, and apply innovations to real-world challenges. Enhance your career, expand your network, and contribute to a better tomorrow. Visit grss-ieee.org and join a technical committee today.
Welcome back. Today we're speaking to Dr. Caleb Robinson, a principal research science manager in the Microsoft AI for Good Research Lab. Caleb has given us a basic overview of what machine learning in the geosciences is. He's also shared how it enhances our work in disaster relief, identifying whales in the ocean, and land cover land use change. Before the break, we started to touch on his work creating Torch Geo, and also his position that satellite imagery should be treated as a different modality for machine learning. So let's jump back in to learn more. Okay, so I want to back up a bit before I ask about Torch Geo. Why do you think satellite data should be treated differently from a standard image modality when it comes to machine learning research?
If you think about images that you might capture with your phone that would make up the vast majority of images in common computer vision benchmark datasets like COCO or ImageNet, those are going to be very different in structure than images that are taken from a satellite orbiting Earth. For one thing, satellites will capture many different channels over different bands than your camera on your phone would capture. The imagery that you get from satellites is at a wide variety of different scales. So some images might be very high resolution, allow you to see detail like cars, trees in a city. Other images are very, very low resolution, are used for monitoring large scale events like hurricanes, and spatial resolutions there can get high as like 2,000 meters per pixel. It's really about the structure of what's in the image, how those images are captured should govern the ways that you model those images. And you can treat from a kind of computer science, computer vision point of view, a pixel is a pixel is a pixel, and just apply existing methods. If you throw a CNN with 8 input channels instead of the normal 3, train it on a bunch of remotely sensed imagery and high resolution labels or high quality labels, it's going to do really good. At the same time, incorporating the knowledge of how that data was captured, what it means, the structure of it, should allow us to produce better models. And those better models are actually vitally important for a wide range of downstream tasks and sustainability, monitoring progress towards the Sustainable Development Goals, tons and tons of reasons why we want to model things from remotely sensed data. And the better that we can do any of those tasks, the better it is for the world. So I think one of my arguments would be, let's use as much knowledge as we can about satellite data, how it's collected, what it means to build better models that can then be used to improve our understanding of the world.
And how will a focus on improving SAT-ML lead to innovations or new discoveries in geoscience work?
Yeah, just one example off the top of my head is the way that rotation is modeled in these algorithms. So things in the natural world have a natural orientation to them. Whereas if you look at satellite imagery, it doesn't have a natural orientation to it. So any way that you observe something in a satellite image, any rotation of it should be equally likely depending on kind of what you're looking at. So being able to incorporate that kind of property into the modeling process should allow you to produce a better algorithm.
Right. And can you give me a more concrete example of how you've worked differently with satellite imagery?
Yeah, I think maybe a very simple one that I've found improves performance when you're modeling with satellite imagery is to not cut up the satellite image into nice squares ahead of time. So a common context method of modeling with natural images, camera images, is to make a bunch of images that are maybe 256 pixels by 256 pixels, create a large data set of millions of them, and then feed them to a model, use them to train a model. Satellite images are huge images that cover large swaths of land on the Earth. 10,000 by 10,000 pixels is a common size for a Sentinel-2 scene. And if you can chop that up ahead of time before you do the modeling step, then you're going to lose a good bit of information about what you're actually looking at. So my normal modeling process is to sample patches randomly on the fly from the larger data sets. And just doing that gives you better performance.
I find this really interesting because similar to your approaches with SATML, during your PhD, you took the leading machine learning pipeline, PyTorch, and you started to code so geospatial data could be used in computer vision pipelines. And this interest led you to co-create Torch Geo, which is a huge asset now. So can you tell us about Torch Geo? What was your motivation and how did Torch Geo come to be?
Yeah, I think the motivation has been acknowledgement that satellite data has a lot of peculiarities that a computer vision researcher that's just getting started in the field might not be aware of and would trip them up when they're actually going to train models. So TorchGeo is a Python library that aims to make it simple for computer vision researchers to use geospatial data and for geospatial data experts to use sort of computer vision AI ML pipelines. So we implement a lot of data sets that are common in the Earth observation field. We have abstractions that allow you to do what I was just talking about, randomly sample from large satellite imagery scenes rather than chop everything up ahead of time, and pre-trained models, transforms that make sense, modeling methods that make sense for geospatial data, all within kind of a well-maintained Python package. This was really started by Adam Stewart. He did an internship with our group, I think in early 2022. So I was his internship mentor, and he's the amazing software developer, and really brainstorming what we could do at the intersection of software and GeoML. We started creating this package, TorchGeo, and it really took off during his internship. We were using it right away and has grown a lot since the end of his internship too.
And how is TorchGeo accelerating the current geospatial or EO research environment, especially as an open source tool?
Yeah, so I think it's getting a decently wide adoption. Last time I checked, it was used in over 100 different GitHub packages that are configured in a certain way such that GitHub knows that that package is depending on TorchGeo. I think it was used in the NASA IBM Prithvi model. We use it internally in our group for almost every GeoML project that we do. So it's been kind of incredibly helpful to us. One of the things that maybe I'm most proud of about the TorchGeo library in general is that I found a paper written entirely in Spanish that was comparing TorchGeo to something else. I don't speak Spanish. I saw it in the citation list, but I was like, wow, it's really crossed geographic boundaries.
It's pretty cool to see that kind of uptake on the team's work, Caleb. Where's TorchGeo going next?
So there's a massive amount of work to do. It's nowhere near done. I don't think it'll ever be done. As new satellites come out, new data sets are created. There's always going to be things to add to TorchGeo. But yeah, it's just been amazing seeing kind of the community that has built up around it. There's kind of many contributors to the library that are not myself or Adam, and I think that's really, really encouraging to me.
Right. I love your enthusiasm for this work. Now, I have a final question for you. These days, there's a push-pull discussion happening across all fields that are using AI. Basically, the discussion centers around two main sides. One, that AI is good and helpful and will revolutionize our work in positive ways. And two, that AI has significant potential for destruction because of shortcomings like biased data, replacing humans, etc. What are your thoughts on this push-pull argument when it comes to the geoscience and Earth observation field? Do you think AI will be more of a help or a hindrance?
Optimistically, I think it would definitely be a help, but it always depends on what role people are expecting AI to play. And I think if we think of it as a tool that domain experts can use in the progress towards the problems that they care about, it can definitely be a help. It can be a hindrance if we think that it's going to sort of magically solve all the problems for us, because I don't think that's the case. Even in attempts to do kind of these large global models, research has been shown that if you instead focus very locally on an area, you'll be able to produce much better outputs. So it can really be both, and I think it depends on what people's expectations are and how AI is being used. The model's perfect, but it's about how you understand how that model is operating, how you're incorporating it into some larger decision-making pipeline, making sure that uncertainty is taken into account. And there, I think, is where the real value is.
With so much data being produced every day, it's hard to imagine a world without AI and the tools it comes with. To be honest, it is such a relief that we have this technology because it helps us extract useful information in a shorter amount of time compared to doing the work manually. It's important to recognize that not all data is the same, and in some cases, working with it requires specialized tools for more effective management. Like a mechanic needs different tools to fix a car engine versus a bicycle, TorchGeo provides an additional framework and tailored solutions for working with diverse geospatial datasets. But even with great tools like this, there's still room for error. So I'm cautiously optimistic about the usefulness of AI. In our next episode, we'll examine an area of AI that is not as loudly discussed, but that is essential to effective, safe, and useful AI: data quality. Learn more about Dr. Caleb Robinson's work with the Machine Learning Research Group by visiting their website at aka.ms/GeoML. You can also check out Caleb's Google Scholar for the latest updates on his research. We have some fascinating episodes in store for you this season, so don't forget to follow us on Spotify and Apple Podcasts. And send some love to our sponsors at IEEE_GRSS on X and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media. And a special thanks to Manil Maski and Fabio Pacifici for their support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.